This is a video for AQA Discrete Mathematics. This is Binary Operations, section 1.1, where we're looking at the property of operations. Well, in the video, what I hope to be able to do is to define what we mean by a binary operation, and we'll in particular be looking at two types, modular arithmetic and matrix multiplication, as examples of binary operations. The two main properties that we need to understand are those of commutativity and then the second one, associativity. Those we'll both look at later on in the video. But first of all, let's see what we mean by binary. Now, you've probably guessed that with the bi in the name, then it involves two. So a binary operation in essence takes two elements and in some way combines them to give an output. But there are some important rules that we have to do. That firstly, our binary operation has to take two elements from the same set and produce a third element at set. So it's important there that the third element, the output from there, is in the same set as A and B. So examples of that would be, for example, multiplication of real numbers, addition of complex numbers. So you know that multiplication, when you multiply two real numbers together, you get a third real number, and you also know that when you add two complex numbers together, you get a complex number. It's also possible for us to sort of make up operations. So for example, here we have one, A circle B is equal to AB plus 2. Notice this idea of circles. We use all sorts of different symbols to represent binary operations. Circle is quite a common one. Also a star and asterisk are quite common, or little triangles. So we can make something up as long as it follows those rules that if A and B are in the set of integers, then if we multiply them together and add 2, that produces another integer, and indeed it does. So let's consider these then. Matrix addition. Well, matrix addition is fine as long as we take matrices from a restricted set. So for example, you could talk about matrix addition on the set of all 2 by 2 matrices or all 3 by 4 matrices. Because when you add two matrices together, you always end up with one of the same size or the same order. In other words, the matrices that you're considering, the set of matrices that you're considering, must be conformable for addition. A circle B is B minus A when A and B are integers. Yep, this is fine. If you take two integers and subtract them, you get a third integer. What about A circle B is B divided by A? Now that one at first sight might look okay, but there is one slight problem with real numbers, and that is that 0 is an element of the real numbers. So if we're going to use that, then we have a problem, because for example, if we had 0 circle 3, that would be equal to 3 over 0, and that's not a real number. So that this one falls down because of this one element. If we restricted it to real numbers that were positive, for example, so those greater than 0, then it would be fine. So defining the set that you're using is very important. And here are a list of some of the sets we might be using. Now, for example, you'll see the first one is just literally a list. You might list a set of numbers, and we're going to confine ourselves to that particular list. And you'll see this happening in modular arithmetic later on. The natural numbers, counting numbers if you like, numbers 1, 2, 3. Notice the symbol there, it's got a double bar on the n. If you're writing it, again, you just write it with a double bar, just a capital Z for the set of integers including 0. But if we wanted to exclude 0 and just have the positive ones, we could have Z plus, which is those which don't include 0, or Z plus with 0, so the non-negative ones, those that are greater than or equal to 0. And then the symbols for the real numbers is R, the rationals, Q, quotient, so this is A over B, and the complex numbers that you've met in other areas. So those are the sets that we might be dealing with in binary operations. Well, let's turn our attention to some specific examples. Here are two that are defined. These are both examples of modular arithmetic. So when we're looking at the remainder after a normal sort of operation of your arithmetic, this is what we call modular arithmetic. So A plus B, when it's divided by 8, then we're looking for what is the possible remainder. And in the second one, triangle is A multiplied by B when it's divided by 5. So we would say that the first one is addition modular 8, and the second one is multiplication modular 5, or just mod 5. And we're going to be here using numbers that are in Z plus, so the positive integers. So we want to say that 2 circle 9 is equal to 2 triangle 9. So what we'd need to do then is to work out what each of these is, of course. So 2 circle 9, well, to do that we're going to have to add 2 and 9. So 2 plus 9 is 11, and 11 divided by 8 is equal to 1 remainder 3. So it's the remainder that's important here. So 2 circle 9 is equal to 3. And we can look at 2 triangle 9. Well, here we've got to multiply, so 2 multiplied by 9 is 18, and now we're dividing that by 5, and 18 divided by 5 is equal to 3 remainder 3. And again, it's the remainder, so that is 3 as well. So these are both equal to 3, therefore 2 circle 9 is equal to 2 triangle 9. Second part of the question is saying, what happens if we wanted to look at all the possible values of A circle B? So if we're doing a division by 8, so we're taking two numbers, adding them together, dividing by 8, then we're saying what is the possible remainder. So that will be equal to something remainder, and it's this part here that we're interested in. So it's just a case of thinking, okay, if I divide by 8, what are the possible remainders? And I'm sure you can see that they are 0, 1, 2, 3, 4, 5, 6, or 7. If we are dividing by 5 in the second one, then the possible values of a triangle B must be equal to 0, 1, 2, 3, 4. Because if we get to 5, then it obviously is a multiple of 5, and therefore will be remainder 0. So those are our possibles. In general, when we're looking at a remainder, looking at a modular arithmetic, it's going to be 0 up to n minus 1. I've already mentioned that these were examples of modular arithmetic, and you can see here just different ways that might be written. So we might have 16 plus 7 equals 3, and we just write in it afterwards mod 10 in that particular case. So 16 plus 7 is 23, so mod 10 it would be equal to 3, which is the remainder when we divide by 10. Sometimes it's done with a plus symbol and then the modular part written after the addition, so that would be modular 8 addition, and similarly underneath there the same idea gives us that's modular 4 multiplication. So just convince yourselves that those sums are correct then. 7 plus mod 8 5 is equal to 4. So 7 plus 5 is 12. So modular 8, that gives us a remainder of 4. Indeed it does. 7 multiplied by 5, 35. Divide by 4, 8 remainder 3. So 7 multiplied by 5 modular 4 is equal to 3. So that's defined the idea of a binary operation. In particular looked at some examples using modular arithmetic. Now these two terms that we need to consider. Commutativity. Commutativity is where we can swap the order around so that A circle B is B circle A. So you'll be familiar with your normal arithmetic things which are commutative. It simply means that you can literally swap the order around. So here a couple of examples. One which is addition. We can have A circle B is simply A plus B, where A and B are natural numbers, for example. That would be commutative. But if we had a triangle B, where that's equal to A minus B rather, then that's not going to be true if we've got A and B are, for example, integers. So for that we can clearly see that let's say 6 minus 2 is equal to 4, but 2 minus 6 is negative 4, so they're not equal, and in fact that's generally going to be the case. For addition, for subtraction rather, and multiplication you may have thought of as being ones that were to be considered. Multiplication is going to be commutative in general. Division isn't. And you've already met the idea with matrix multiplication that matrix multiplication is not in general commutative. Well, here's a proof that we've been asked to do that would show that this operation is commutative. Now, two ways of doing this. You either start off with the operation as defined and then show that it is equal to the operation done in the other order. Now that would be a case of rewriting this as y plus x and minus yx, because both addition and multiplication are commutative. So we can do that. We know that for normal multiplication that those are and normal addition, they are both commutative, and this is just equal to yx by definition, y circle x. The other way of doing it would be to show that y circle x is equal to the definition for x circle y. I mean, so basically we're showing that sometimes we start off with the left hand side and the right hand side and combine them to show that they are equal to each other. Sorry, not combine them, rearrange them to show that they're equal. So because normal addition and multiplication are commutative, then that defined operation there itself is commutative. Associativity is the property that we can put in brackets in any place, so we can change the order in which we combine things. Again, something that you'll be very familiar with from your arithmetic. You know that if you're doing 2 multiplied by 3 multiplied by 4, then you can put the bracket in first, so you can do that as 6 multiplied by 4 to give you 24, or alternatively you can do 2 multiplied by 3 multiplied by 4, and so we get 3 times 4 is 12 first. These are entirely the same as each other, so normal multiplication of numbers we would say is associative. It's not necessarily true for all types of things though. So we've looked at an example there where it is associative, so we could say that A circle B is equal to A multiplied by B, where A and B are equal to real numbers. Then yep, that is associative. But what happens if we were to do division of the real numbers, let's say excluding 0? So would that work? We'd need to exclude 0 from the discussion we had earlier, but no, it doesn't. So this, if we had A triangle B is equal to A divided by B, then this isn't associative. So for example, we just need to find a counterexample, don't we? So using 6 divided by 3 divided by 2, for example, well, 6 divided by 3 is 2, so that gives you 1. But if I do it as 6 divided by and then 3 divided by 2, then that's 6 divided by 1.5, so that's 4. They're not equal to each other, and therefore these are not associative. So to prove something is not associative, then it's usual just to do it by finding some example that doesn't work. So for example, we could do 2 star 3 star 2 would be fine. Let's try that and see what we get. 2 star 3 is 2 to the power, so if we're doing the bracket first, 2 to the power 3 star 2. 2 to the power 3 is 8, so this is the same as 8 squared, which is 64. But if we do 2 star 3 star 2, then that's the same as 2 star, and then we've got 3 squared, so this is 2 to the power 9, and that's equal to 512. So there's just one counterexample to show that it's not associative. That's the end of this introduction to binary operations. In the next video we'll be looking at something called Cayley tables.